Today we're going to look at our central limit theorem. Instead of looking at our central limit theorem for sample proportions, we're going to look at our central limit theorem for sample means. Right, so in the last section we reviewed some vocabulary, we looked a little bit at our definitions of accuracy and precision, reviewed some of our notation, and we also got a new formula for finding the standard error of our sampling distribution of the sampling mean. In this section, we're going to revisit our central limit theorem that we originally saw back in section 7.3, and we're going to use the central limit theorem to do calculations for our sample means. All right, so to start with, the figure below shows the distribution of in-state tuition and fees for all two-year colleges in the United States for the 2012 to 2013 academic year. Note that it is skewed and multimodal. Right, so when we're dealing with things for central limit theorem, remember that we needed a curve that was a normal curve. Right? It was unimodal, it was symmetric, it was more of a bell-shaped curve. Right, so what we're going to do, instead of using our distributions for populations, right, we're going to look at distributions for our sample mean. Right, so our figure below shows the distribution of the sample mean for sample size of 30 and 90 drawn from the skewed multimodal distribution that we saw above. Notice the shape of each is approximately normal and the standard error decreases, right? Our curve narrows as the sample size increases. Right, so again, we're not going to think about drawing directly from populations. Instead, we're going to look at distributions of our sample means. Right, so in our first example, below are three distributions. One of these distributions is a population. The other two distributions are approximate sample distributions of the sample means of randomly sampled from the population, one of sample size 10 and the other of sample size 25. Match the graph with the correct distribution. Okay. So if we compare these three different graphs, right, the one that changes the most, right, the one that is not normal, right, that is going to be our graph of our population. So that means that the second image, right, we're going to say this is the graph of the population. Right, because it is not a normal curve. Right. Then if we look at the other two curves, right, both of those are approximately normal. We know that as our sample size increases, our graph becomes more precise and it narrows. Right? So if we compare the two that are left, this bottom one is more narrow, right, than our top one. So we would say this is the graph of the sample size of 25. Right? It is normal with, right, less spread. Right? It is taller and narrower, means there is less spread or less variation. Right? So that means that this is the graph of the sample size 10. Right? It is still approximately normal, but it has more spread. So it is normal with more spread. Right, so as you're going through and as we're thinking about these different problems, as we saw in previous chapters, as we saw in previous sections, right, the size of our sample is something that is an important factor to consider as we're doing these problems. Okay, so now we're going to revisit our central limit theorem. Again, we first saw our central limit theorem back in section 7.3. Right? Our central limit says if certain conditions are met, Right? The central limit theorem tells us that our distribution is approximately normal no matter what the shape of our original population distribution. So even though in that previous example our population distribution was nowhere close to being normal when we looked at our samples, because they were large enough, because the conditions held, they were approximately normal. If the population is normal to begin with, the sampling distribution is exactly a normal distribution. If it's not normal, then it's an approximate. The larger the sample size, again, the better the approximation. Right? The larger the sample size, the more precise, the less variation, the lower the standard error, and all of those things go together. All right, so our conditions for our central limit theorem. Right? The sampling is random and independent, so another condition that we've seen in previous chapters. Again, we're going to assume this is true unless we are told otherwise. That we have a large enough sample. So we're going to look at two different things. Either the population distribution itself is normal. If that's the case, then our sample size won't matter. Or if our sample size is not, or if our population distribution itself is not normal, then our sample size must be large enough. And instead of doing a multiplication like we saw in previous chapters, we're just going to check the amount. As long as our sample size is at least 25, we're going to say that 25 is a large enough sample. Right? A population, our population must be at least 10 times larger than our sample size. Right? Then we're going to get a sampling distribution, and it is going to be a normal distribution. In section 7.3, when we saw this normal distribution, we used, instead of mu, we used p, and we used our standard error, which came from a formula that had a square root and some different p's and some subtractions and things in it. In this case, our sampling distribution that we're going to use, right, our mean is going to be our population mean, so it's going to be mu, and then we're going to use sigma divided by square root of n to find our standard error. All right, so let's work through an example. According to data from the National Health and Nutrition Exam Survey, the mean weight of 10-year-old boys is 88.3 pounds with a standard deviation of 2.06 pounds. Assume the distribution of weights is normal. Right? So here we are told that it is normal. Suppose we take a random sample of 30 from the population. Can we find the probability that the average weight of the sample will be above 89 pounds? If so, find it. If not, explain. All right, so we start with our population. Right? So our population is going to be all 10-year-old boys. Right? Our sample size, there were 30 that were sampled. Right? Our mu is our population. Right? So according to the study, the mean weight of 10-year-olds was 88.3 pounds. So our mean, 88.3 pounds with a standard deviation of 2.06 pounds. Okay. All right, thinking back to section 7.3, when we were writing out what we wanted to know, here we used a P for our notation, right? P being the probability. So what is the probability that the average weight will be above 89 pounds? When we were doing ones in section 7.3, we saw P, and then we had a P hat inside. Well, we're not talking about a proportion this time. We're talking about a mean. So this time we're going to put an X bar inside. Right? And this particular question asks, what is the probability that the average weight of the sample will be above 89 pounds? So we're going to use a greater than or equal to, and we're going to use our 89. Okay. Now we're going to check our conditions. The sample is random and independent. We are going to assume that that is true. A large sample. Technically our sample is large enough, but if we look back to our question, it says that this distribution is normal. So I'm going to just say here, the probability distribution is normal. So sample size does not matter. Right? It is also above 25, but in this case we just need to check and see if it's normal. Right? Our large population, right, is all greater than or equal to 10 times 30. Right? our population size is definitely larger than 300. So all three conditions are satisfied. Okay. All right, now we're going to find our normal distribution. Right? And as we're looking at our normal distribution, our first value, right, is our mu. So we look back up here, our mu, our mean is 88.3. So that's going to be our value that goes right here. Okay. Right, and then our standard error, we're going to take sigma divided by the square root of n. So our sigma was 2.06, and we're going to divide it by the square root of our sample size, which is the square root of 30. This gives us a decimal, rounded to 3 places, 0.376. Okay. Now we're going to take this information and we're going to go to StatCrunch. Right? We're going to use the exact same thing we used in Chapter 6, and we're going to use the exact same steps that we used in Section 7.3. We are going to go to our normal calculator. Right? And when we go to our normal calculator, right, we are going to want to make sure that we enter things correctly. Right? So for our mean in our normal calculator, we're going to use this 88.3. For our standard deviation, right, we're going to use the standard error that we just found of 0.376. And then we want to make sure that we select, right, x is select the greater than or equal to, and hit the 89, enter 89, and then hit the compute button. Right. So thinking about our curve here, our 88.3 is here. 0.376 gives us kind of small values as we're going out. Once you do the calculation in StatCrunch, it'll also give you an appropriately shaded curve. Unlike what we did back in Chapter 7 at this point, I'm not going to take the time to carefully label my axes. We should have a pretty good idea of what we mean by normal probabilities at this point, and especially since you guys aren't turning anything in on paper, it's okay if you just kind of approximate the curve and think about what area is going to be shaded. Right, so to answer our original question then, so the probability that the mean of the sample is greater than 89 pounds is about 3.1%. Right? And that's the value that gets, right, given to us in StatCrunch. So after we hit the compute, right, this is the value that we have. Right? That's the answer then that we get for our probability. Right? So similar setup to what we saw back in Section 7.3. Again, the big difference is here we're looking at means instead of proportions. So instead of everything being proportions or percents, we have different means, and our standard error formula is also slightly different. All right, so let's look at another example. Home prices in a certain community have a distribution that is skewed right. The mean of the home prices is $498,000 with a standard deviation of $25,200. Suppose we take a random sample of 30 homes in this community. What is the probability that the mean of this sample is between 500,000 and 510,000? Right? So in this case, our population is all homes, right, in the community. Our sample size, right, is 30 homes were sampled. Right, our population mean, right, is 498,000. Right, our standard deviation, 25,200. Right, what we want to know. We want to know the probability, so then again we're going to use our P. We're asked what is the probability that the mean of the sample is between 500,000 and 510,000. Right, so this is going to be a case where we're going to use our between probabilities. Right, so again, instead of having a p-hat, we're going to have an x-bar. but we're going to sandwich it with less than or equal to signs, our smaller value on the left and our larger value on the right. Right, now we're going to check our conditions. The sample is random and independent. Yes. Do we have a large enough sample? In this case, our population is skewed. So we do have to check our sample size, but our sample is greater than or equal to 25 because our sample size is 30. So we are good. And we will assume that there are more than 300 homes. Right? 10 times 30 is 300 homes in this community. Okay. Now we're going to find our normal distribution. Again, our n, right, is our normal distribution. The first value in here is our mean. Our mean is 498,000. Right, now we need to find our standard error. So we're going to take our 25,200, our population standard deviation, our sigma, divide it by the square root of 30, right, and we're going to get $4,600.87. Okay. All right, so now we're going to go to StatCrunch, and we're going to use the information that we just found. Again, we're going to use our normal calculators. Right, for our mean, we're going to enter in this 498,000. For our standard deviation, we use our standard error, this 4,687. And then we're going to select between this time, right? And we're going to type 500,000, right, less than or equal to our x bar, which is less than or equal to 510,000. And that's going to give us a value of 0.327, which is 32.7%. Okay. So looking at our normal curve, right, we are thinking about these being between 500 and 510,000. So we're going to have a value somewhere over here, right? So we have a between area that's shaded in. Again, this is not an exact sketch, not as good of a sketch as we did back in chapter 7, but at this point, as long as you have the basic idea of the sketch, that's good enough. So we're between 500 and 510,000. Again, in StatCrunch, we're going to be given a similar image, and then we're going to finish off this problem by saying the probability that the mean sample price is between $500,000 and $510,000 is about 32.7%. All right, so again, we're making a list of what we know, we're checking our conditions, then we're using our mu, right, our population mean, then we're finding our standard error, and then we're going to our normal calculator in StatCrunch, just like we did in chapter 6, just like we did in section 7.3 to finish these problems off. All right, on this last page, we're just going to revisit examples 2 and 3. We're going to slightly change our question that's being asked. So looking at example 2, our population was all 10-year-olds. We had a sample size of 30. The big thing that's changed here is in this particular problem, we're looking at a random sample of size 10. Right? So I'm not going to go through and list everything that we did previously because our mean is still going to be the 88.3. Our standard deviation is still 2.06. Right? We're still looking for the same thing, the probability that our x bar is greater than or equal to 89. I'm just going to kind of focus in on these two problems on our conditions. Okay, so our sample is random and independent. Yes, we are always going to assume that that is true. Right? We take a random sample of 10, it's random and independent. Do we have a large enough sample? Well, if we look at this, our sample size is only 10, but our actual distribution right, was normal. So in this case, we're going to say the distribution is normal. Sample size does not matter. All right. So if our original population distribution is normal, as it is in this case, our sample size does not matter. Do we have a large enough population? Right? Is all greater than 10 times 10 is 100? Right? Our population is definitely large enough. So even though we have a small sample size here, even though we have a sample size of 10, our distribution of weights is normal. Right? So since our distribution was normal, we satisfied our second condition. Okay, so then to finish this off, again, we're going to use some information that was listed out on the previous example or that we can find in the paragraph above. Right? Our mean, our mu, is 88.3. To find our standard error, we're going to take 88.3 divided by the square root of 10. Right? That's going to give us 0.651. Right, then we're going to go to StatCrunch. We're going to go to our normal calculator, right, just like we did before. We're going to enter in this value instead of our standard error that we saw in example 2. And then we're going to do our calculations. Our sketch is still going to be an area shaded to the right. So our probability using StatCrunch, again, I'm not going to list out everything that we're putting in, but we are using StatCrunch to find this probability. Right? The probability that the sample mean is greater than 89 pounds is about 14.1%. Now if we compare this value to our answer to example 2. In example 2, right, our standard deviation was smaller. Our standard deviation was 0.376 instead of this 0.651 that we have. Our standard error, I should say, excuse me. Right, in this case, our probability in example 2 was 3.1%. Since our standard error is larger, right, that's what causes our percentage to be larger. So I'll just make a little note in here. This is larger than the previous answer to example 2 due to the larger standard error which was a result of the smaller sample size. All right. So our probability that our sample mean is greater than 89 pounds is about 14.1%. Again, it's larger than our previous example due to our larger standard error, which was in turn a result of our smaller sample size. All right, now we're going to do the same thing. We're going to revisit example 3. So as we're looking at this one, right, home prices in our certain community, right, have a distribution that is skewed right. The mean was 498,000, standard deviation of 25,200. Suppose we take a random sample of 10 homes in this community, right? Can we find the approximate probability that the mean of the sample is more than 510,000? If not, explain why. So slightly different question that we had in example 3, but what we are going to look at, again, we're going to start with kind of our focusing on our conditions. Right, so is our sample random and independent? Yes. Right. As we look at our other information, notice that we have a random sample of 10 homes in this example. Right. And notice that our normal distribution was skewed right. Right. So in this case, Do we have a large enough sample? Well, our distribution is skewed right, right? And our sample size is 10. 10 is not greater than or equal to 25, right? So our sample size in this case is not large enough, right? So at this point, we're just going to stop. We can't continue. We can't answer this question because we have not satisfied our conditions, right? So can we find the approximate probability that the mean of the sample is more than 510,000? No, we cannot, right? So we're going to explain why not, right? And we're going to say we cannot answer the question because the conditions are not satisfied. Okay. So if we start with the normal distribution, our sample size doesn't matter. If we are not specifically told that we start with a normal distribution, then we do have to check these conditions. Again, generally, if there's going to be a problem, it's going to be that our sample size is not large enough. Right? So as you're working through these problems in this section, pay attention to the vocab that's being used, pay attention to the notation that's being used, and make sure you're checking your conditions as you're going through your problem.